Hi, my name is Qiao. I'm from City University of Hong Kong. In this video, I will introduce our work, how the common retention acceleration method of 3D NAND flash memory goes wrong. I will first introduce the flash retention acceleration method that is widely applied, and then through a one-year retention evaluation, I will then present how this method is not correct on 3D NAND flash chips. Next, I will present the real long retention errors and some discussions, followed by the conclusions of this work. The number of applications is greatly increased in these years. This trend causes high I/O pressure on the storage systems, in our case SSD devices. Current 3D flash memory-based SSD has been evolved from 2D to 3D to provide higher storage density and better performance. To provide even higher storage density, the solution is increasing number of vertical layers of 3D NAND flash memories. NAND flash memory stores charge in flash cells and represents data based on the threshold voltage of cells as shown in this example. And several types of error sources will impact its reliability, such as program recycling and retention time. And retention errors is one of the most important flash errors, which are caused by charge leakage over retention time. To guarantee the reliability of stored data, the flash controller provides error correction codes that are strong enough for the robust error rate after a long retention age, for example, 1 year. However, it is can consuming to observe the retention errors over a year or even longer. In practice, high temperatures are applied to accelerate retention effects because high temperatures increase the mobility of electrons. Arrhenius law is widely applied through baking flash chips at a high temperature to obtain the equivalent retention effects to that of a low temperature. Based on the law, we can calculate the baking hours if we want to know the retention effects at 20, 25 degrees for 1 year. For example, as shown in the table, we need to bake at 60 degrees for 97 something degree hours or 100 degree for 1.6 hours. We conduct evaluations on real 3D NAND flash chips to study the retention acceleration method. This is our evaluation platform and 4 3D flash chips are evaluated. The experiments were conducted over multiple temperatures. For 1 year retention at room temperature, flash chips are placed in the office with air condition and the temperature is set at 25 degrees. For high temperatures, we calculated the baking hours according to the law as shown in the last slide. Through the evaluations, we will present 5 new findings that are contrary to our common beliefs. Our first new finding is that the errors through baking with high temperatures significantly underestimate the real long retention errors. The upper blue line shows the robust error rate at 25 degrees for 1 year, which is the real long retention errors, and the other lines shows the errors through baking with high temperatures. We can see from these two figures, one charge trap flash, one floating gate flash, the real robust error rates after 1 year retention time are much higher than those through baking with high temperatures, more than 20 times in some cases. Our second finding is that the difference between the real and estimated errors on 3D floating gate flash, this one is floating gate, is smaller than that of 3D charge trap flash. This is because the retention acceleration method is developed in the 2D flash generation, where most flash chips are based on the floating gate cells. While today's 3D NAND flash memories many adopt charge trap technology as the fundamental flash cells. The acceleration parameters and models that used to be adopted on 2D floating gate flash chips introduce less deviations on 3D floating gate flash than that of 3D charge trap flash. Our next finding is that the difference between the real and estimated retention errors changes with the number of program and read cycles. When the number of program and read cycle is small, for example, when the raw bit error rate of high temperatures, these four bars are very similar to that of 25 degrees the real retention errors. With the increasing of number of P cycles, the difference between 25-degree and high temperatures becomes larger. The reason is that during the lifetime, flash chips endure a large number of program erase cycles, and every program erase cycle will introduce high voltages, which introduce oxide degradation and flash cell damage. After enduring different numbers of P cycles, flash chips could present different retention characteristics. The above three findings are made regarding the overall errors. Then we discuss the errors introduced by different read voltages. We use TLC as an example. Each TLC stores 3 bits in the cells, and there are 7 read voltages to differentiate 8 voltage states. Errors could be introduced near every read voltage. For example, these two voltage states may overlap, thus V4 may introduce errors. To read an LSB page, one read voltage that is V4 is applied, while two read voltages for CSB and 4 for MSB. According to existing work, we know that higher voltage states suffer more from retention errors because they have higher voltages. Thus, different pages will have different errors because they require different read voltages to read data. So our fourth finding is that the temperature affects the raw bit error rate variations among read voltages as well as flash pages. As shown in this figure, at 25 degrees, the difference between low voltage states and high voltage states are very large, while at high temperatures, 80 degree, 100 degree, the difference is much smaller. And the variations among read voltages also affect the variations among pages, the lines in the figure, as reading each page requires one or several specific read voltages. For the QLC flash chip, there are 15 read voltages and 4 flash pages. The variations among them are also changed. They have very large variations among these 4 pages at 25 degrees, but the difference is much smaller when the temperatures are higher. Our last finding is that the temperature affects RBR raw bit error rate variations among word lines. The raw bit error rate of different word lines inside the same flash block. This is the word line index in a flash block. The raw bit error rate of different word lines presents significant variations, which come from the physics structure of 3D flash blocks. Such variation has been reported by previous studies and considered as constant. However, in this work, we found that such variation is not consistent, especially CSB and MSB page when the temperature is changed. For example, at 25 degree, the MSB page of this word line has the highest raw bit error rate, while at 80 degree high temperatures, The CSB page of this word line has the highest repeat error rate. Based on above findings, we can conclude that the error behaviors over a long retention time at low temperatures are very different from those through baking with high temperatures. As a result, we cannot achieve the equivalent error behaviors. Then, as current long tension errors are all estimated through baking with high temperatures, we first present the real retention errors of 3D flash chips over 1 year at room temperature, that is 25 degrees in our case. As printed, as printed earlier, the error rates introduced by higher rate voltages are much higher, and the charge trap flash has much higher error rates than floating gate flash chips. Based on our evaluations, current retention calibration method is not correct, which will impact the flash reliability estimation as well as the reliability optimization method. Therefore, we need a new retention acceleration method for 3D NAND flash memory. Finally, the conclusion of this work. We conduct a 1 year retention evaluations on real 3D NAND flash chips, and we have studied that the real error behaviors at low temperatures are very different from that of through baking with high temperatures. And we provide the real long retention errors on 3D NAND flash chips. Thank you for watching this video. If you are interested, welcome to my session for online discussion.